All right, so we had talked about, any questions from the stuff that we've gone over last Wednesday? Okay, cool. So we had finished up talking about properties of different estimators. Again, this is going to be helpful as you start to get into methods literature and doing different types of things. They'll talk about when you start to get into some of the nuts and bolts of different statistical procedures. They'll say, well, we could, some people will use this, but it turns out under these conditions, that estimator is no longer efficient if these types of things go on. These are terms that'll come up, and so wanting to have at least a decent background and sort of understand what some of this stuff is going on. And what ends up happening, and why this starts to become important, is some of the next things we're talking about. You can plug whatever you want to in a regression analysis, and SPSS will give you numbers. Now, whether or not those numbers mean anything, or whether you can have any confidence that your statistical tests map on to what you think they do, is based on whether or not you've met assumptions. And so when we start screwing around with assumptions, we start to worry about the properties of these estimators, right? So we talked about ordinary least squares, unbiased and consistent in the presence of collinearity, but no longer efficient, okay? What we see is that our standard errors created in OLS, when we have very, very strong correlations between predictors, OLS isn't an efficient estimator, right? We still, relative to some other types of estimators that we have, variability in that sampling distribution of our standard errors, or that sampling distribution of our test statistic, ends up being larger with OLS than it will be for the other stuff. And so then it's no longer an efficient estimator, right? So depending on, and this will be a big thing, not just identifying, oh, this is a violation of an assumption, wanting to know what the consequences of that violation is for your tests, your inferences, and things along those lines. What is that side of stick? Okay, there we go. So basic assumptions of our regression models. First thing we're going to talk about is our assumption that our predictors are fixed non-random variables without error and variance greater than 0. What types of things strike people? Anybody surprised by this as an initial assumption of our regression models? Are we happy with this? Is this something that we're like, oh yeah, sure, no problem. This is not an issue at all.
What do you mean by fixed?
Okay, we'll talk about fixed stuff in a moment. But yes, that starts to be tricky. What's the other thing that stands out for people? Measured without error. Our assumption under regression is we're assuming some error in our outcome variable. But in order for regression to work the way that it's supposed to work, we're assuming that we've measured our predictors perfectly, without error, right? Do we do this? No, we don't do this, right? But we conveniently forget about this and then just pretend like it's not there. But this is a statistical assumption of these regression models. Other thing here is the assumption that our predictors are fixed. Does anybody remember what a fixed, what's the difference between a fixed variable and a random variable? Fixed values, right? So if I'm running an experimental study and I have condition 1, 2, 3, and 4, that's a fixed variable. There are only 4 values. I, as an investigator, at determining who's in each one of these conditions, that's a fixed variable. What's a random variable, Sam? Right. Random variables, height, weight, anything we plug into the front end of a regression model, right? They're things that we come through and we observe, and we're assuming a random distribution. We have no control over what those specific values are. But from a technical standpoint, from original development of regression, we're assuming fixed, non-random variables measured without error with variance greater than 0, which means that your predictors just can't be constants, right? Okay. We're also assuming that our errors are normally distributed. We're assuming that once we predict the difference between our predicted values, say this is my predicted value for everybody with X value of 2, right? I'm assuming that if I were to take a look at the distribution of my errors, right, the difference between my predicted value and my actual observed value for everybody who had an X value of 2, we're assuming that those errors have a natural distribution. Okay? We're assuming that for the most part we're going to be pretty close. Some people we're going to overpredict, some people we're going to underpredict, but in general those errors for every single person who has any possible value of whatever X we have, we're assuming that those errors follow a normal distribution. We're also assuming that the variance of our errors is constant for all values of X. Okay? This is our homoscedasticity, or this is our homogeneity of variance assumption applied to regression, right? And again, this is based on our residuals, right? So we're assuming that variability around our errors for someone who, all the people who score 10 on our 0 to 100 scale for our predictor, has the same, those errors have the same amount of variability as everybody who scores 90, right? We're assuming that the difference between our predicted values and our observed values for every single of X is going to be identical, okay? We're assuming that our errors are independent, okay? So that the residual of case I is independent of individual residual of case J. I'm assuming that the difference between my predicted value and my actual observed value, and the difference between Sam's predicted value and his observed value, and the difference between Morgan's predicted value and her observed value are completely independent of one another. Okay? We have design issues that start to go through and fool around with this, which is why we need to transition into things like hierarchical linear models, or excuse me, HLMs and other types of approaches that deal with nested data. Okay, we're also assuming that our errors are uncorrelated with our observed predictors, right? So whatever level of the predictor you have has no relation with your errors for that everybody with that level, and then we expect the expected error in the population is going to be 0. Okay, our expected value for the residual is going to be 0 for everybody in the population. Okay, so we're going to walk through each one of these, but these are your fundamental assumptions of our regression models. Okay, some of these things we can test in our data, and some of these things we can't test. Some of these things are going to be violated 100% of the time, right? And so we want to know what the consequences are, what are our workarounds, so that we can start to address some of these, so that we can still have reasonable inference based on our results. Okay? It's never a good thing, right? When you make, oh, here are my assumptions. I know straight off the bat, even before I start collecting these data, I'm going to violate 6 or 7. Not hopefully not that, but so wanting to know what the consequences of these are. So basic terminology you'll hear within regression literature. Estimates referred to as blue, the best linear unbiased estimates when we meet assumptions 1 and 3 through 6. So as long as we have fixed non-random variables, heteroscedastic errors, independent error with each other, independent error, errors independent of observed X, 0 population error, these are circumstances under which we would identify our estimates as the best linear unbiased estimates for blue. If our residuals are homoscedastic and independent of one another, You'll hear this referred to as IDD, independently identically distributed errors. Okay. These are just common terms that come up in regression literature. You'll want to know what they're referring to. Okay. So our normality of errors, our normal distribution errors, if we're going to estimate our errors unbiasedly in ordinary least squares regression, okay, we need to make sure that our errors have a normal distribution. That means our residuals have a normal distribution around for every predicted value of x. If we fail to achieve this, our standard errors are going to be biased. And Angelina, what happens if our standard errors are biased? Yeah, why?
Because it's the denominator.
Yeah, right. This is the stuff that's going into the denominator of our statistical test. And if we've overestimated our standard errors, what's going to happen? Yeah, we're going to have too conservative a test, right? We're going to reject the null more than we probably should. What if our standard errors are too small? Inflate, right? We're going to have test statistics that are too big, right? And so this is and same thing with our confidence intervals, right? If our standard error is too big, our confidence interval is too big. If it's too small, our confidence interval is going to be too small. This is the primary concern. If we start to violate a lot of these assumptions, our estimates, right? Our point estimate of our various coefficients aren't impacted. They're fine, right? But what we start to see impacted is our standard error estimates. And so even though my point estimate isn't bad, my inference on whether or not this is reliably different than 0 starts to get thrown one way to the next. Okay? And so our normality, normal distribution of errors is a big piece of this. Okay? And so when we violated our assumptions, two things we're worried about. What is this doing to estimate of the population regression coefficients, right? Just like the mean, the population mean is some unobservable number, right? Some unobservable value out there. The same thing for any one of your regression coefficients, right? In the population, if we were to run this model in the population, what would that be, right? We want our estimates, that our point estimate of that value to be unbiased, as taken from our sample. If we violate our assumptions, what's the impact on our coefficients, and then what are the impact on our standard errors? Okay. These are the two things we need to start thinking about in terms of violating assumptions and the consequences for what we make of our different tests. Questions about this? All right. So, working through these fixed effects. Okay. So this is our number one, our first assumption. We're assuming that predictor variables, all of our x's, right? Maybe we only have one x, but maybe we have lots of them. We typically will with the regression model. Fixed non-random variables without error and variance greater than 0. So within this fixed effects model that we're assuming for our regression, we're assuming that as who was saying, Angela was saying this, we're assuming that our predictors have specified values that are specifically included in the sample, and in the sample we're capturing all possible values that could be captured in subsequent replications, right? So even if, let's say, I am looking to regress some outcome on age, in a fixed effects model, right? If I'm saying this is a regression model looking at adults, right? That a fixed effects model would say, I specifically go out and get someone of every single age. Let's say that if we're rounding to the nearest number, I would have systematically gotten 5 people, 10 people from every possible age from 18 to however old people live, right? That would be a fixed effects. That would be, in this example, age would be a fixed effect. And we find with our fixed effects of regression makes no assumption regarding the distribution of your predictors, right? Because if I systematically sample 10 people of all possible ages of adults, what does that distribution look like? What do you think, Katie? Yeah, so if I were to systematically sample age so that I had a set number of people from every age, what would my distribution of age look like? Yeah, it's just a square distribution, right? Does that look normal? No, right? And so from a fundamental standpoint, regression makes no assumption about the distribution of your predictors. It can be whatever they want, right? All we're assuming is that our predictors are fixed, non-random variables measured without error and with some variability greater than 0, right? How often do we do this in a regression model? Never, right? So right off the bat, we've already violated this. And so if you want to think about the difference between fixed effects, random effects, if I'm looking at, yeah, I was just trying to, thank you, Candace. But let's say I want to look at the relation between like gumball flavor and taste or enjoyment or something like that, right? And I know that there are 7 different flavors of gumball. What I go through and I do is I go through and systematically gather however many I want in my sample from each flavor of gumball, right? This is a fixed effect. These are all the gumball flavors there are in the universe. Anyone who goes through and replicates this is going to have these same values for the gumballs, right? Now, if I go through and I start randomly selecting gumballs, if these aren't gumballs, if these are people of different races and ethnicities in the universe, and I'm just randomly selecting these people out, some of my replications aren't going to have equal representation of all these different people with these different characteristics, right? If I'm running a random sample of intelligence, I just get my sample and I go through and I measure IQ scores. I haven't captured every single level on this predictor across all possible, I may be missing people on the low end, I may be missing people on the high end, right? I have no control over where people are coming in, right? Now, if I were to go through and say within a sort of 5-point range, say here are 20 people in this range, 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 then I have a fixed variable, right? But this typically isn't how we go through and sample, right? So we're not saying with our fixed effects that we have this natural distribution where assuming most people are in the end. We've systematically sampled all possible values of whatever predictor it is that we're looking at, okay? We always violate this, okay? But what ends up happening is our estimates remain unbiased if our variables in the model are multivariate normal, okay? So this goes back into what we had talked about previously in the screening, right? We're talking about variables that are multivariate normal. Hard to test this directly, but we assume that we've reasonably approximated multivariate normality if all of our variables have a reasonably normal distribution, and all bivariate combinations between our variables are linear and homoscedastic, right? So all that stuff that we talked about before about looking at bivariate normality or multivariate normality, this is why this is important, because we always violate this fixed variable assumption. But this is why we have to go through and systematically test, look at our individual distributions, look at how they're related to one another, because if we have data that are multivariate normal, then the fact that we violated this fixed effects assumption doesn't impact our inferences. Okay? I did a review of a paper where these people, and understandably so they had submitted a review paper. They're very up in arms about why people are always hyper-focused on distributions of variables in regression papers, and because technically for regression there is no assumption about the distribution of variables, but we see all these papers that continue to be upset and run transforms and things like that because they don't have predictors that have a normal distribution, and how this was a clear misunderstanding of the test because we didn't have to do this, right? Well, going on with this is a de facto assumption unless all of your predictors are fixed effects or fixed variables measured without error. If we violate that, then this does become a thing that starts to become important, right? So I'm going to show you what I tried to frame as a kind way of saying your entire premise is without merit because this is important because of these other things, right? But this is why I want you all to be sort of knowledgeable and at least exposed to this, so when this types of things comes up, right? If you have a very nice screening piece in your manuscript about why all the steps you went through to go through and screen and make sure that your data assumptions for regression, and someone says, that's nonsense, you don't need to do that, there are no distributional assumptions for regression, you're like, well, there are, because I haven't, my predictors aren't fixed effects or fixed variables like anybody else's, right? So people understand the difference between fixed effects or fixed variables, random variables here. Yeah?
So there's errors when your variables are not fixed. Is that what the error means? Like,
Error is a different thing, okay? We're also assuming, so the fixed variable is one piece of this, the measured without error is another piece of it, okay? If we're taking a classical approach to looking at measurement error, a classical approach says any value of x that I get, right? I have you step on a scale, and my variable of interest is mass, right? I get an estimate of your mass, and that estimate of your mass is some product of a true score plus or minus error, right? If I have you on a very sensitive digital scale, this error term is very small. Right? If I go up and grab you around the waist and pick you up and just gauge how heavy you are, that's a much less precise estimate, right? My estimate of how much of your mass is going to be a value, right? But it's going to be made up of your true mass plus or minus some error, right? Error term is much bigger on this, all right? Same thing, if I have a good, well-validated measure, my estimate of the true score of whatever construct it is that I'm trying to get at is probably going to be a lot closer than something that I just come up with, or a single item scale that tests how extroverted you are, right, or something along those lines, okay? And so if we have measurement error within our model, measurement error in our outcome variable, measurement error in our y, doesn't provide any bias in our parameters, but it does start to inflate our standard errors. So the extent to which you have a crappy measure of whatever your outcome is, okay, our parameter estimates are still going to remain unbiased, but our standard errors are going to get bigger, right? And again, if our standard errors are going to get bigger, Lauren, what does this do to my test of inference? What's that? It deflates them. So is it harder or easier to detect effects? Okay. So again, we often don't merge in our methods and our statistics, but for the types of things we do, we are all interested almost universally in things that aren't objective, things that we can just measure, right? We're interested in psychological constructs, and we do have varying levels of success in measuring these psychological constructs. And right, you say, oh, you know, I should think about measuring my outcomes well, just because that's a good scientific thing to do. It also helps you detect the effects that you're looking for, right? You can think about this as having a direct impact on your power. If your outcome variable is measured using some harebrained measure that you just came up with on the fly, you're going to have a harder time getting the effects you want because you got much more error in whatever it is that you're trying to test, right? Or if you have an option between a validated and psychometrically sound measure versus the first one that you found in a paper that you read, right? This is where this stuff starts. There's a practical impact on this. It impacts your power, right? No one likes to run a study and not find anything. This is one of the things you can do to start going through making sure that you're optimizing your chance of detecting effects that you think are there, okay? So measurement error in our outcome, we can have it. It just makes it harder to detect things because it tends to cause more static, inflate our standard errors. But we do get bias in our parameter estimates when we do have measurement errors in X, okay? When we measure X with error, this is when we start to bias those coefficients that we're starting to look at. And if we think about the relation between X and Y, okay? We can think about your relation, or your coefficient for the regression of X on Y as a function of your population parameter times your reliability, okay? And so what ends up happening with this equation So what happens, Stephanie, when if this is your population coefficient and this is the reliability of your predictor, what ends up happening when we measure our predictors without error? If we measured our predictor without error, what's the value going to be for this reliability coefficient? Yeah. What is it, Katie? It's going to be 1, right? And so if we measure our predictor without error, what's our predictor going to be, or what's our coefficient going to be here? Okay, so this is why this is, right? If we measure our predictors without error, and this is the assumption of regression, that we measure our x's without error, right? Based on this formula, this value is 1. That means that my estimate that I get is going to be, on average, equal to my population estimate. Right? Now, what happens when my reliability starts to get worse? Gets further and further away from the population. Which direction? What's up? Up. So if a perfect reliability is 1, what is less than perfect reliability? It goes down, right? So if I take my population coefficient and I multiply it by 0.8, right? Because that's a good this is excellent reliability. 0.8 is an excellent reliability estimate for any variable, right? What happens if I take this value and multiply it by 0.8? What happens to my outcome here? It goes down, right? And so what ends up happening, if we measure our predictors without error, then we say that on average we expect our sample coefficient to be equal to our population coefficient. But as we start to measure our predictors with error, it systematically suppresses our estimate of our reliabilities, or excuse me, our estimate of our coefficient, right? So if this relation is 0.8 in the population, let's say this, our population coefficient is 0.8 and I have excellent reliability, right, is 0.8. What is my corresponding estimate of that regression coefficient? What do you think, Morgan? If this is 0.8, because that's my population effect, and that's 0.8 because I have excellent reliability, what's what I expect my point estimate to be here? It would be 0.64. 0.64 is not 0.8, right? That's a much smaller value, right? And so when I run my analysis, I say, oh, the relation between x and y, the unique relation between x and y is 0.64. When it's actually not, it's 0.8, right? But what I've done is I've introduced measurement error into my predictor, and so it's systematically suppressed that, right? So this is not something we can deal with. The best we can do is try and get the best measure that we can. But knowing that we are measuring our predictors with error in applied regression, we should probably expect that this is going to systematically underestimate the true population just because we're throwing more static into the mix. So fixed effects, we violate fixed effects assumption. We're good as long as our variables in the model are meeting assumptions of multivariate normality. But we start adding error variance into the measurement of our predictors. Our resulting estimates start to become smaller and smaller. They get systematically shrunk, and that shrinkage is a direct function of the extent to which we've got a messy measurement of our predictors. Okay, and so this is why it's so important when people are like, oh, well, this is kind of a good enough thing, right? Or I kind of just did the best I could with this type of issue, right? We're fighting underestimation and the likelihood that we're not going to detect effects that are there, and we have to then make this up with increasingly large samples in order to detect statistically reliable effects. Okay. So this is kind of an important thing. Again, we don't talk about it, right? You don't read a paper that then starts marching through to the extent to which they violated fixed effects assumptions or measurement of their predictors without error. But you know, when we get regression out of the package, right, this is what came with the model, and so it's important to know what happens when we start to violate that stuff. Questions about any of this? All right. Assumption number 2, our normal distribution of our errors. Right, we're assuming that for all values of x, our errors are demonstrating a normal distribution. Okay. If we take a look down at this graph right here, we're saying if this is my data, right? This is my predictor x, this is my outcome y, these are my data, here's my regression line. I'm saying that for every possible value along this x, continuous x, if I were to go up and look at my residuals have a normal distribution. Most of them are pretty close. Most of my values are pretty close to my predicted value. They start to spread out, fewer and fewer out on the tails. But for each and every value of x, I have equal distribution around that regression line. Okay. Important for tests of significance, multiple correlations, regression coefficients, right? So testing your your unique predictors, right? Your unstandard regression coefficients, your multiple correlations, your R-squareds, making sure that our inferences based on our statistical tests are reasonable and accurate is predicated on this assumption that our errors have normal distribution across all values of x. Okay? We can get problems in terms of our non-normal errors in terms of sometimes if we our sampling strategy is bad, right? Let's say so we're looking at the impact of depression and functioning, right? And we only get people who are pretty severely depressed. What can happen then this is functioning, and this is high, and that's higher, right? We would expect that to see a relation between depression and functioning, right? But if this is our functioning variable, we might end up with a regression line that looks something like this. No, other way. Something like this, right? Yeah. But what might end up happening is we get right? But here, so you've got a big, so most of your people are up here. But, and so this is, you're pulling the regression line up here because this is where most of our values are at, right? So it's pulling things up here. But when I'm wrong in terms of the relationship between severe depression and functioning, I'm not overestimating people's level of functioning. I'm always underestimating, or excuse me, I'm never overestimating people's level of functioning. I'm never underestimating people's level of functioning. I'm always overestimating it, right? So here, even though most of our people are fitting this line, when we miss, our misses are systematically below what we would expect. Because this person right here, they're not as high as function, or they don't have as much depression as this person, but they're still not doing good, right? They've still got low levels. And so what we've got here is we could imagine a scenario where we end up with, So our regression line that's running here, but when we're predicting too high, right? We're systematically overestimating functioning across this, and so what ends up happening is we've got non-normal errors in this situation. So again, this might be an example of how we could have a sampling issue that could lead to non-normal errors, or we might have just in the relation between X and Y, it just may not be have normal residuals here, right? Heroin use in children, right, is not going to be, it's going to be zero for the most part, right? But there's going to be some kids out there who have it, right? And so we're always going to be, when our errors are, when we're missing, we're always underestimating as opposed to sort of catching those people up there, right? And so this is the type of thing, and we'll go through and talk about different techniques where we can start to look at our residuals. And so this is what this might look like in a bivariate case, but as we start layering in multiple predictors, then we have to transition into multivariate space, which starts to get pretty tricky. But from a basic standpoint, in terms of our errors, this is what we're assuming, is that for all values of X, when we're missing on Y, sometimes it's above, sometimes it's below, but we have normal distributions on these misses. Questions about this? Okay. Again, our regression coefficients are unaffected, right? Our estimate of the population coefficient is not going to be impacted by violations of normality in terms of our errors, but it's going to depress the standard errors of our regression coefficients. Okay. And again, Alex, what happens if we depress our standard errors of our regression coefficients? If I depress my estimate of a standard error of a regression coefficient, what are the consequences of that going to be for my inferences? Right, my standard error is going to be lowered. So what am I going to? What's the mistake that I'm going to make with this? What's that?
It's going to be
Inflated, right? So we're gonna claim significance. We're gonna be like, oh, this is a reliable coefficient, or this variable within the context of this model holds a unique relation with outcome, when maybe it doesn't. Maybe it does, but maybe it doesn't. But what's happened is I have non-normal errors, and then standard errors are too low, which are going to make my test statistics too high, and that's going to be a problem, right? And then when we get small samples, it start to depress the standard error of my R squared, so that I'm saying that I have a statistically significant model when maybe I shouldn't be claiming that, or I'm going to claim a statistically significant model more often than I should be, given my error rates, because non-normality has suppressed my the estimate of my standard errors. Questions about this? Okay. Other thing that we have in terms of our assumptions, we're assuming constant error variance, right? Here we're saying that for every value of X, not only are our errors normally distributed, we're saying that our variance is equal across each, or the variance of my errors is going to be equal across all values of X, right? What I'm saying is that if I'm looking at low values of X, my errors are distributed here. At high values of X, my errors are distributed about the same. What I don't want to see is something where right, so here I've got this, here, whoops, not that, I've got something much higher, right? This falls back into that that homoscedasticity assumption that we had talked about previous, okay? Difference between homoscedasticity, as we talked about primarily on in terms of the context of regression, is we're focused on our residuals here, okay? Previously, we're saying we're looking at observed scores. What we're going to do when we start screening through our regression models is we're going to want to make sure that it's not the relation between X and Y in a regression line, what we're going to be looking at is our residuals in multivariate space. Are our residuals normally and equally distributed across all values of our predictor? Okay. And again, measurement error can produce heteroscedasticity, also omission of relevant predictors, right? We talked about this before. If I'm looking at the relation between income and age, I'm going to get heteroscedasticity in there, right? What am I missing in that equation, Lauren? If I'm looking at age and income, and I see a fanning pattern in terms of that data, what variable do I need to account for in that if I want to look at that relation? So I find that as people get older, they tend to make more money, right? But I see that at the low end of age, I see very little variability. At the high end of age, I see a lot of variability. What do I need to account for? What am I missing in that? Education, yeah, right? I can be quite old, but if I don't have education and a career and things like that, I might still be making the same amount as a very young person because, right? And so we start to see this. And so these are the types of things and why it's important to go through multiple levels of looking at things, because this is what happens sometimes, right? People will say, identify a heteroscedastic relation between X and Y, or X1 and X2, in just the general multivariate screen, looking at bivariate plots, right? But in multivariate space, if I've got a variable that accounts for why we have some of that, my residuals might be wonderfully distributed, right? And in that case, then I'm not worried about it, right? Because I've got something in there that's accounting for that. So again, one of these things, even though we may see homoscedasticity in a bivariate relation between two people, or between two variables, once we get that within our regression environment and are looking at our residuals, we might see that situation resolves and that's no longer a concern, right? But then that starts to become an interesting thought experiment. Okay, I saw X and Y, or X1 and X2, demonstrate a clearly heteroscedastic relation, but I'm not seeing heteroscedasticity within my residual screenings. I wonder what it is about, what else is in the model that's helping account for variability with increasing values of one relative to the other. Okay? So good things to keep you awake at night. So in terms of thinking about impact on our analyses, once again, our regression coefficients are unbiased. Right? So your point estimate of your relation or unique relation between your predictor and your outcome, that's fine. That's not a bias. That doesn't end up being affected by heteroscedasticity. What ends up happening is we see bias in the direction, in general, bias in the direction of that heteroscedastic relation. So if our error variance increases as our predictor increases, right? If I get a situation like this, right? What ends up happening is I depress my standard errors, right? As my X values get bigger, my variances get bigger. We end up with standard errors that are too small. But if my error variance decreases as a predictor increases, kind of get the opposite thing going on. We've got a bunch of variability here, and then it narrows down here. What we can get is inflation of standard errors in that situation. So once again, not just identifying that, yeah, I have heteroscedasticity, what do I do about that? Going through and recognizing what the potential impact of this violation is on my inferences that I may have. Okay. So questions about normality of errors and constant errors. Cool. All right. We're assuming independent errors. Okay. We're assuming that the difference between my observed value, my predicted value, has no relation between Stephanie's predicted value and her observed value, right? These are completely independent of one another. And when we start to see dependency in our residuals, when we start to see our errors start to become correlated with one another, something that in the regression literature you hear is termed as autocorrelation. The observation of my error for me is similar to Alex, is similar to Morgan is similar to Katie. There's some sorts of autocorrelation in there. A couple different types that we can think about. If I'm looking at observations drawn from the same person over time, right? This would be some type of longitudinal study or repeated measures study where I capture Alex and have her measured 1 time, 2 times, 3 times, 4 times, right? If we've got a time series study or an EMA type of study, you can absolutely bet that you're going to have some form of temporal autocorrelation here, right? And we'll get into this in terms of our repeated measures in our mixed ANOVA models. Sam and I have talked about this a little bit, just looking at a model like this. The problem is we start to get violations of assumptions, or violations where if I've got 2 observations that are closer to one another, they're going to be more highly correlated than observations that are farther apart, right? So if I look at Katie's values at time 1 and time 2, and time 1 and time 3, those values are going to be much more closely related than values between time 1 and time 10, and time 1 and time 15, right? Those are going to be much less related than those that are closer related. So what we've got is a situation we would identify as temporal autocorrelation, right? And this makes sense. We know why it would happen. It just creates a violation of assumptions of certain types of statistical models. Right? We can also see observations being correlated among individuals who are sampled within different or within similar environments. We call this spatial autocorrelation. For anybody who does education research, right? If we're working with our HLM models and things like that, these data that have nested structures, right? I'm interested in looking at the impact of an intervention, a reading intervention in classrooms, right? And so I go through and I randomly select different classrooms to get the intervention, other classrooms not to get the intervention, right? But in addition to differences in reading instruction, these are all kids that are in a similar classroom, having a similar environment, working with a similar teacher, getting the same type of instruction, even though it's the same program, they're all getting the same version on the same day. And if the teacher gets sick and a sub comes in, that's impacting all of those people. And so what we get is the relation of my score and Stephanie's score, if we're in the same classroom, is probably going to be more closely related, or the difference between the predictor, and in this case we're talking about residuals, right? So here's what I think everybody who got the reading assignment should be scoring, or the reading intervention should be scoring. But the deviation from my score from what they expect and what Stephanie's score is from what they expect, probably going to be more correlated if we're in the same class than if Sam was in a different class, right? And Sam had a better instructor than Stephanie and I did. And so he's actually, his score is a lot closer and more closely related to Lauren's and Alex's and Angeline's, because they're all in the same class, right? And so we've got spatial autocorrelation that we have to account for in those types of designs. Now, what we do about these is we typically recognize that this is an issue, right? And so you just can't stuff that type of data into a regression model and expect reviewers to say, sure. We've come far enough along in terms of our method where people start to recognize certain types of designs as inherently problematic for certain types of analyses, and we can go through and make adjustments to that. But if we were to do it, once again, regression coefficients are going to be fine, but again, our variance estimates are going to be biased. Our mean squared error and our standard error regression coefficients are going to be substantially underestimated, right? Because we've got correlations there. We're getting less variability because everybody's kind of in the same, everybody got the same intervention. They're also all part of the same classroom. That's going to shrink down the variability, and it's going to make things look a lot better than they probably should be if we're accounting for various forms of autocorrelation here. Okay. People sort of understand conceptually kind of what's going on with these. So this is more of a design issue. This isn't something that we necessarily probably need to worry about in most of our designs, if we're just having people come in, we're assuming people are filling out their questionnaires independently of one another, not talking with each other, but something to keep in mind is a design feature. Independent errors, okay? We're assuming that our residuals are uncorrelated with our observed values of X. This is going to be a direct product of correct specification of your regression model. We've got these little asterisks up here. This is something that we can't test in our data, right? By definition, estimation of your regression in OLS will create uncorrelated errors. But if that's an artifact of your method and not something that actually is a function there, then we've got problems. But we can fix and make sure that we don't have problems with dependent errors if we correctly specify our models. And our models are going to be correctly specified if we've included all relevant predictors, we've excluded anything that's not relevant, and we've correctly specified the form of our relation. So is this something that we should worry about? What do we think? Lauren, is this something we should worry about? What's that? No. No? You don't think we should worry about it? We often don't worry about it. Okay? When was the last time someone specified a correct model? Think about this. This is a high bar, right? I'm trying to predict non-suicidal self-injury, right? Candace, what types of things should we be thinking about in a correctly specified model to capture non-suicidal self-injury?
In a correctly specified model?
Yeah.
Couldn't tell you.
Right? What types of things would you think that you should take a look at?
History of self-injury, negative affect, personal distress,
Stuff like that, right? Lots of different things, right? Is this often how, particularly if we're running secondary analyses, how we often construct our models? No, what's going on when we're doing secondary analyses, Angela?
single variable.
Yeah, maybe these are the data that we have available to us, so these are the things that we'll punch into a regression model, right? So I could have 6, 7, 8 different variables that for a correctly specified model I should probably have in there accounted for, but we didn't collect those data, and so I'm not going to do that, right? And this starts to become sneaky and problematic because we start running into this third variable problem where we can't explicitly test this assumption with our data, right? But what ends up happening for people in different fields, and so I have friends over in like econ, right? This is a huge thing. Talk about third variable bias, and sort of this isn't actually related to this other thing. It's this third variable that's actually causing this relation, and so you think it's a relation between availability of health insurance and this other thing, but it's actually not. That relation is actually just a proxy for this other variable that's causing a problem. And so if we looked at errors, we would see that the value of your errors and how far you are off in your residual is actually correlated with what level of your predictor that you've got going on. And so this starts to be a huge, huge issue for certain areas. We conveniently ignore this in psychology, but it should be something that we're more concerned about. Because often in like econ, right? Like I can't create different countries with different economies and manipulate their GDP and things along those lines, right? And I can't go to the government of South Africa and be like, I would like you over the next 20 years to collect these data because I have a study that I'd like to run, right? With certain fields, what they have to do is go through and try and find what variable, what data is out there that they can get to test what they're trying to get at. And so then this starts to become a huge issue. And in psychology, we can technically say, oh, I'm running this study. I want to say, oh, these are the things I'm interested in looking at. I can collect this from a sample and then run my model. That's often not how our research works, right? Probably maybe at least half of it is like, we have these data available to us. Let's go through and see if what's the unique relation of X1 and X2 on an outcome, when there are probably 7 other variables that we need to have in there in order to have a correctly specified model. And so it's unlikely that anybody in psychology will ever spike your paper because they are making an argument that you have violation of, that you have dependent errors. But it's something that you as responsible researchers should be thinking about in terms of putting together your thesis, your dissertation, and things along those lines. What are the relevant factors? What are the things that I need to have in here that are then in here so I can go through and have at least some confidence that I haven't made some sort of violation somewhere in the background. Other thing too, right? You can't just go through and say, oh, I'm going to have these 15,000 different predictors I'm just going to dump in there. We can't have things in there that we don't need either, right? And so wanting to think carefully, know your literature, understand what types of influences seem to be important from a theoretical and empirical perspective on this, and thinking about how do we go through and build our models so we don't have weird stuff going on. Okay? This is a theoretical issue. It's not testable, right? I can criticize your model to the extent that you've got 2 things in here and have omitted all the things that are important. And I don't trust the results of your analyses, particularly if they're telling me something that's weird and counterintuitive. This is something we want to be thinking about on the front end, okay? Really complicated, like complicated impact of, in the background, having correlated errors, or your errors correlated with your predictors. Hard to say. All aspects of estimation, your standard errors, your parameter estimates, things kind of go nuts, right? So again, this is kind of scary to think about, but something you should keep in your mind in terms of when you're writing your analysis and reviewing papers, and if someone's got a paper that does some screwy, that they've got sort of a relatively minor predictor of an outcome and have omitted all the important things that should be going on, sort of questioning whether or not this is a true effect or maybe a function of a poorly specified model. Another thing that we can't test is zero population error, right? We're saying with this regression equation that we've put together, right? This is my model. If I were to run this model in the population, the expected value of error is going to be 0. So on average, right, my predicted values are going to be equal to the actual observed values in the population, right? Now we know that's always going to be not the case. We're going to have some variability, but on average, the expected value of error in the population is going to be 0. Okay. When we run things in OLS, it guarantees that the average sum of our residuals is 0. Like if it's not, that's the whole purpose of the estimator, right? You can't run a regression model in OLS and not add up all your residuals and have it be equal to 0. It does that by definition. But that doesn't mean that we have 0 error prediction in the population, right? We can start to get biases here, right? So for example, I go through and I measure everybody's weight with a scale that's 5 pounds heavy. Okay? What's going to end up happening is I'm going to have a biased estimate of my population parameter, specifically the intercept, right? My estimate of the relation between height and weight, because let's say that's what we're doing in this studies. We're looking at the relation between height, diet, and body type or something like that in predicting weight, right? And I'm measuring my outcome with a scale that's systematically 5 pounds heavy, right? The unique, my estimate of my predictors, right? My 3 predictors, my intercept, everybody's going to be 5 pounds heavier than what I would expect, right? And so my intercept, if I'm interested in that, there's not zero error in my estimate of population. If I run that in population, my error is going to be off by 5, or my intercept is going to be off by 5, right? Now this is a case where we might not be too concerned with this, but let's say we're looking at playground aggression, right, in terms of number of occurrences, and we're monitoring how often kids go and physically strike, push some other child, right? But we find that if I'm out there and this is my thesis, right? I'm one of Cynthia's students, right? And I'm sitting down and I'm sort of making the track and keep track of who's hitting who. If this is an infrequent occurrence, pretty easy, pretty reliable to get that. If everybody's hitting everybody, yikes, right? I can't keep track of who's doing what, right? My estimates start to become much less reliable. And so what ends up happening is I start to create systematic biases where I can't be certain that if I were to run this model in the population of all children, that I would end up with zero estimate or zero error estimates in terms of my outcome. I'm going to end up with systematic bias in my outcome here, right? So my residuals, so if this is the model that I run in the population. Here's sort of my estimate of where I'm at. Here's my population over here, right? I've got systematic sampling error in that. Yeah.
So this violation is related to like measurement error basically, because then if you're off, it's because of measurement.
To some extent, yeah. So measurement errors, again, one of these things that can go through and start to create biases here, right? And this is the problem with this stuff is that we can't test this. We don't know this, right? Because once again, OLS makes sure that the distribution of errors or the average error in our sample that we've run is 0. Like that's kind of its function. That's what it does, right? The problem is this can be going on, and unless we're being careful with our methodology, we can't test this and say, oh well, I'm 5 points off the population estimate. Right? I mean, if you could do that, then you wouldn't need statistics, because then you just go, this is the population estimate, right? And so again, goes back to this idea of being very, very careful and planful in terms of how we're putting our studies together, how we're measuring things. People will get aggravated, like, oh, this is wonky technical stuff, it's not a big deal, it all washes out in the laundry anyway. That's systematically not true, okay? This stuff does have an impact, right? We might like pretend it doesn't have an impact. Again, I'm going to rename this sequence all the uncomfortable things that we like to forget about in research, but there's something to keep in the back of your mind, okay? So here, we can have violations of parameter estimates, standard errors. Typically not super serious, and it's not something that we typically get too worked up in the context of psychological science, but it is one of these things that we want to keep an eye on and think about. And you will see people in other areas, again, particularly like econ and other sort of poli-sci types of things, where people start to get, you see more, this type of thing start to get more airtime. Questions on any of this? Okay, cool. Let's take a break, Greg. All right. So yeah, pop open that file. Sorry, I thought I had that posted up there. We'll jump into that, and then also make sure that you have your standard multiple regression in this screen out, because we'll jump into that in just a moment. So, talking about our assumptions. Got those under control. What we want to know is how we go through and start to take a look at these within the context of the models of interest. So our fixed effects, right? Our violation of our fixed effects assumption, we can ignore this, right? This has no impact on our inferences as long as our variables are multivariate normal, okay? And we're going to assume that our variables in our model are approximating multivariate normality, are normally distributed and homoscedastic, okay? So if we go through and we take a look at the linear combination or the bivariate relations between all of our variables, homoscedastic relations, and all of our variables have some sort of approximate normality, or at least don't have evidence of severe non-normality. When those two conditions are met, we'll assume that our data are reasonably meeting criteria for multivariate normality, and so we can ignore any impact of the violation of fixed effects, which happens almost 100% of the time. Okay? Unless we were using a regression model to go through and look at like an ANOVA analysis or something like that, which we could do quite easily, but most of the time we'll just go through and run those in a environment that's going to make sense to people who are trying to communicate that to. We're also going to take a look at our linearity assumptions involving normal heteroscedastic errors, looking at some residual plots. Okay, in SPSS, what we're going to do is we're going to look at the scatter plot of our standardized predicted scores on the x-axis and our standardized residuals on the y, right? So this is going to give us kind of a straight line of what we're hoping at. These are our predicted values. We're hoping that our residuals are sort of normally distributed around that axis, okay? Concerns with our independent errors. Once again, these are going to be focusing on designs where we know that we systematically violate this. Nested structures, repeated measures, designs that have autocorrelation and things along those lines. So if we're looking at our list of assumptions, fixed non-random variables, we can ignore this as long as we can make a reasonable argument for multivariate normality. Distribution of our errors, we're going to look at our residual plots. Independent errors, we can take a look and reflect on our design that we're using, try to make sure that we haven't done anything crazy there. Independent error, zero population error, these aren't things that we can actually test explicitly. So, residual plots. This is an example, and did people go through, read the screening chapter in Batch and Fidel? Show of hands who did that. You gave dip your Candace, in my line, that this is not the best one of the best chapters in a statistics textbook you'll ever read. Chapter 4 is Batch and Fidel, the screening.
It's very helpful.
It is incredibly helpful. Also the regression chapter, very helpful. I don't hold you guys accountable to this stuff. I'm just encouraging you. This will make your life a lot easier if you go through and read these before you start jumping into some of these things. You can spend 10 hours trying to figure out what the hell's going on with some of these assignments versus maybe the hour and a half that it'll take you to work through the chapter. A much more efficient way to get a handle on some of this stuff. So again, make sure to go through and do that. But they'll go through and talk about procedures for looking at residuals. And one of the things, as I said, we can do, we can have our predicted values along our x-axis, our residuals on the y. If I have residuals that are normally and independently and identically distributed, this is kind of what it looks like, right? We've got our predicted values here. We've got most of our residuals are kind of lined up closer to around this line, with then residuals kind of falling out and sort of getting down. So if we're thinking about this as looking at a series of normal distributions, looking from the top down onto this, this is kind of what we would expect to see within the data. Okay? People kind of see what we're looking for here. We're excited about this. Panel B, we have non-normal residuals. All right. Here's our predicted values. Right. Most of them are stacked up around here pretty tight, and so this is why we've got a regression line going. This isn't a regression line, but if we were to have a regression line, it would look like something like this, right? This is why we don't have something down here, because this is where most of our data is, but when we miss low, right? And so we've got non-normal residuals. would look like a pattern, something along those lines. Nonlinearity, right? This would be an example of where we might see nonlinearity in the data. This would be, in general, 9 times out of 10 or more. If you've got nonlinear relations, you're going to see that in your bivariate relations, right? You'll see x and x1 and x2, and you'll see some sort of weirdness in terms of that. But things start to get complicated when we get into multivariate space, because there could be something about the unique combination of x1, 2, and 3 with our outcome that then produces some nonlinearity that we may not have expected. We're going through, if we start to look at our residuals, we could see something, I mean, this would be an extreme case. I've never run into this before, but it would suggest that there's something going on with the combination of those variables that's holding a nonlinear relation with my outcome, right? And so even though it looks like there is a very clear relation between the best linear combination of these 3 variables and my outcome, I might not capture that in a linear model, right? So important to take a look there. And then panel D, we've got heteroscedasticity. Okay? We're seeing that our predictions are pretty good at low levels of our predicted value, but as our predicted values get higher and higher, let's see, this is functioning, right? And we're looking at a bunch of different things that are predicting functioning. When we're predicting low levels of functioning, we're pretty good. When we start to get high predicted levels of functioning, we're way off, right? We haven't violated our normality assumption, right? Here it looks like our residuals remain normally distributed across levels of our predicted value, but by the time we get here, we get much more variability in our residuals at high levels of my predicted value than low levels of the predicted value here. Rule of thumb for trying to glean something, sort of determine whether or not this is an issue or a non-issue. I mean, this is a pretty clear case here. But what we would want to see is situations where the spread is 3 times greater at the widest versus the most narrow. That clearly is a situation here, right? We've got clear and systematic errors. Now, in the examples we'll do today, for the sake of maintaining sort of consistency across the data set we're using, our residuals are going to look weird, but hopefully, but as you get into problem set 3, you're going to get variables that have more cleaner. It's hard if you got 24 people in your 24 observations in your analyses to try and identify systematic stuff going on, but this is in general kind of the types of things we're looking for in our residual plots. Questions on any of this? Okay, cool. So if we were to do this in SPSS, what would this look like? Again, this is not a great example because this is our model with 24 predictors, or 24 observations and 2 predictors. But if we wanted to get our residual screen we go analyze, regression, linear, and then we're going to select plots, and we're going to put our Z predicted and our Z residuals for X and Y, and this is the residual plots you're going to get. This looks a lot sadder than these ones, right? But again, we've got 24 observations. What we want to do here is on the 0 line, draw a 0 line here, right? And depending on sort of how intense I'm good at, like sometimes I'll just paste that into a Word document and literally just draw a line across that 0 mark so I can get a sense for where things are at. And what I want to do is take a look and see, do I have, is there evidence of nonlinearity? Do I have evidence of normal distribution of errors? Do I have evidence of homoscedasticity of line errors? Right? And here, this is kind of hard to tell, right? If I go through and draw this line here, right, it looks like I've down here, maybe more variability than down here, but it's hard to see when you've just got maybe one point going on. We've got these 2 cases down here that are looking problematic, perhaps, but I don't know that I would say, oh, I have clear evidence of heteroscedasticity or non-normal errors, but a lot of that is just a function of having a hard time seeing something because you don't have really enough data to have a reasonable regression model in this example. But this is what the plot looks like. This is kind of what we're looking for. Questions about this? So again, when you're looking at these residual outputs, take this line and just draw a line across 0, and what we're looking for is spread of those residuals. All right. Other assumptions, these aren't formal assumptions, these are just general things that will get screwy with your analyses if you have them in there. Outliers, routine screening procedures with our outliers, right? We want to go through and look at on the individual, for your individual distributions, looking at z-scores, your box plots, your histograms, trying to see if there are any cases that are hanging way out there on the margins. We can also identify problematic cases looking at our residuals, right? If we have large standardized residuals in there, it means we've got a case that this cases where this model isn't doing a good job of predicting, right? So here, we've got 2 standardized residuals that are less than -2, right? Depending on now, for this case, there's only 24 people there, so I'm not getting too worked up about most of that. But if we were to see, say, a nice plot like this, and then a case like hanging out way the hell down here, that might be a good case to want to take a look at and see, boy, we've got a couple of people who this just isn't doing a good job with. So wanting to take a look at that, so in addition to our univariate screening, look at our residuals, also multicollinearity singularity, right? Singularity just being an extreme case of multicollinearity, where this combination of variables is redundant with another variable or set of variables. Rule of thumb for our bivariate correlations, we see bivariate correlations between our what's going into our model at 0.9 or above, but that's way too high. Like if you're getting anywhere even close to something that looks like that, you've got redundant measures in your analysis. You want to go through and start making a decision on, do we need these? Do we need all of these? Can we kick these out? The answer to that is always yes, because if they're correlated that highly, they're the same thing. But evidence of our tolerance values anywhere between 0.5 and 0.6 can still start to be problematic. Remember, when we start to get high levels of collinearity, it starts to screw around with our standard errors, inflate our standard errors, and we want to keep an eye on that. And then if we do have situations where you have highly correlated predictors, want to take a look at your standard errors in your final solution. If there's something that, in the extreme case, what you can get is, say, a predictor that has a standardized coefficient of, say, 0.7, right? And my standardizer, if my standardized coefficient for an individual predictor is 0.7, someone tell me what the interpretation of that would be. Yeah, so I've got a regression model, and X2 has a standardized coefficient of 0.7. What's the literal interpretation I would give to make based on that coefficient? Not quite. Remember, we can't make that interpretation. And so this is just like our unstandardized coefficient, but it's a standardized coefficient. So what does this tell me about the unique relation between X2 and my outcome? Okay, close. What units are we talking about in the standardized for our standardized coefficient? That's true. Okay, so we would say if I've got a standardized coefficient of 0.7, it's saying for every standard unit deviation, for every standard deviation increase that I get for X2, I would expect a 0.7 of a standard deviation increase in my outcome. Okay, so it's the same way we would interpret an unstandardized coefficient. Our units are just standard deviation units, right? So again, 0.7, I would say for every standard deviation unit increase in X2, would expect a corresponding 0.7 of a standard deviation unit increase in our outcome. Right? So that would be the literal interpretation. If I'm seeing a standardized coefficient of 0.7, Lauren, what might I assume about that, the magnitude of that relation? It's a large, right? This is the nice thing. This is what we want within the context of an individual regression model, using that standardized coefficient to be able to look at relative sort of strength of relation among unique relation among my predictors, right? Because it's hard to decipher that from my unstandardized coefficients unless all of my predictors are on the same scale, right? I could have one unstandardized coefficient of 0.02 and one of 50. I don't know which one of those is bigger than the other one because it all depends on the scaling of the variable, right? 0.02 could be p less than 0.0001 and the 50 could be 0.999 in terms of our significance values, right? Impossible to tell based on looking at the unstandardized coefficient unless I have a very good sense for what these scales are, right? My standardized coefficients, I can just look at those. But let's say I see a standardized coefficient of 0.7 and I find that that's not a statistically reliable effect. Should I be concerned by that? Should that catch my attention? Yeah, why is that, Anton? Yeah, it's your standardized coefficients are close to, they're very similar to some of our standardized effect sizes, right? And unless I've got 5 people in my sample, that would be weird. But this is the type of thing we can get when you've got highly collinear relations. You might find that something has a massive standardized coefficient. It's still not statistically significant, even though you got a couple hundred people in your sample, because your predictors are correlated 0.95 with one another or something along those lines, okay? That'll throw your standard errors, it'll inflate your standard errors, throw them all over the place, right? So this is something you want to keep an eye out for. And again, we can have situations where on the bivariate case, correlations between our predictors and all our variables seem kind of reasonable, and it doesn't happen often, but it can occur where a combination of, say, these 3 predictors end up being collinear with predictor 5 or something like that. And this is how we want to look at our collinearity statistics and start to tease some of that stuff apart. So taking a look at our collinearity outputs here, again, under Analyze Regression Linear, we can request collinear diagnostics, case-wise diagnostics, some things we want to take a look at. Collinearity statistics here at the end, we'll get a tolerance and a VIF. These are functionally redundant pieces of information. Just sort of depending on whatever rule of thumb sticks in your head better, you can take a look at one or the other. We want to see tolerance values greater than 0.1 with an asterisk that if that gets anywhere close to anything that small, that should be a red flag long. Well, if you get tolerance values less than 0.1, you start to, SPSS might give you error messages and things like that. Again, remember your tolerance is 1 minus your squared multiple correlation, right? And the squared multiple correlation is going to be the relation of, say, if we take x1 and regress it onto all other variables, the r squared for that, 1 minus that, right? So if all, let's say, variables 2, 3, and 4 together account for 90% of the variability in predictor 1, that would give me a tolerance value of 0.10, right? Because 1, 2, 3, and 4, if I regress x1 onto 2, 3, and 4, 2, 3, and 4 are accounting for 90% of the variability. That would be my r squared if I were to run that. And if we take 1 minus 0.9, does it give me a tolerance of 0.1? That suggests these 3 variables together are highly supercorrelated with this other one, right? So again, tolerance less than 1 or a variance inflation factor greater than 10 are technically, okay, this is problematic. It's from a conceptual standpoint, it's problematic far before you reach those levels. That's pretty extreme, okay? And you, as professionals in your area, should recognize what's going on, where the redundancy is occurring, and go through and address that before proceeding with your analysis. Okay? So this is our collinearity. Other thing we can look at is our collinearity diagnostics. What we want to go through is we can start to see where we're getting, what combination of variables are starting to cause problems. We want to see, we have problems if we've got eigenvalues that start to be close to 0, so you can see your eigenvalues here. Now your last eigenvalue will also often be real small, but if you've got eigenvalues that are asymptotically approaching 0, that starts to become problematic. What we can also do is take a look in, we want to see if we've got a condition index in this column greater than 30, combined with variance proportions greater than 0.5 on 2 or more variables, that's going to start to tell us where some of that collinearity is taking place. So if this, my condition index was, say, 32 here, and I've only got 2 variables, but let's say I've got 5 different variables, right? And I've got a condition index of 32, and this one's 0.8, and this one's 0.6, and another one is 0.55, and then everything else is going wrong. I would say there's something going on with variables 1, 2, and 3 causing these 3 to be highly collinear, right? So I might see my tolerance or my variance inflation factors be really high for those 3 variables. I can go down through and look at this to start to determine sort of what's the combination that's causing problems in terms of collinearity between my stuff. Okay. And then other thing we can go down through here and take a look at is your standardized residuals. Okay. Again, this is, you can interpret these in terms of z-scores and on a z-score scale, right? This is telling you how many standardized, on average, how many standardized units a residual is from the average, right? And so you can see here we've got a standardized minimum standardized residual of negative 2.24, 2.5, an upper of 1.6, 1.7. If we go back to and take a look at this, so here's our ones that are negative 2. Here's our one that's 1.7 up here, right? We can get our minimum and max here, and starting to see if we get very large values down here, sort of similar to what we would expect in terms of multivariate outliers and things like that. We'll look at our monohologous distances, but we can also look at our standardized residuals and start to see what are there cases out there that we're doing a really bad job of predicting their actual observed value. Questions on this? All right. What we're going to do is switch over and jump into our example here. So go through, open up this this exercise. So have that data set open, and we've got our regression handout here. And what we're wanting to do is we're wanting to look at so what we've got here in this regression model. The question is, we're interested in looking at some sort of functioning outcome variable. So we've got our role functioning variable here, ranging from 0 to 100, providing an index of functioning, higher scores equal greater functioning. And what we're working with is a set of individuals who've been treatment-seeking individuals who've been involved in motor vehicle accidents, and we want to take a look and see if we can predict role functioning in these individuals based on continuous severity of accident-related PTSD, our measure of physical pain, and a dichotomous indicator of opiate use. Okay? So I've got 2 variables that we're going to conceptualize as continuous, right? Our PTSD and our pain scale, and then we've got a dichotomous predictor. Opiate use, right? Am I on prescription opioids? Yes, no. I've got a categorical predictor in there. Is that okay? Is it fine to have a categorical predictor in my regression model? If what? If it's dichotomous, right? And always with your dichotomous predictors, code them 0, 1. Just anything that has two values, code it 0, 1, code it binary. Some people will code 1, 2. It's problematic. You'll have to change it eventually. Just code things 0, 1. It makes things easier and helps with interpretation. But this is the model that we're gonna take a look at. So again, to keep in mind here, our linear model is going to be functioning equals beta 0 plus beta 1 PTSD plus beta 2 pain plus three opiate use. Okay. All right. So what we're going to do is, before we go through and run our regression model, we're going to start looking at some basic screening stuff. So what I'm going to do here, so I got participant numbers, pain, okay, so it looks like I have all complete data for my pain variable, complete data for my opioid use, complete data for my PTSD, complete data for my role functioning, right? So I've gone through, made sure that I have complete data here. If I go analyze, frequencies, like an opiate use, this should be 0, 1. There's a way to make that bigger. That didn't do anything. All right, so if we take a look here, we see everything's coded no, yes, right? This is also something to keep in mind when you're working with your own data. If we go through and make sure that we've got categorical values, making sure those are labeled appropriately, that helps a great deal. But we can go through and see what is our conclusion, Alex, in terms of our breakdown of our opiate use here. It's about equal, right? It's about as equal. I think I manufactured this actually. But we got equal representation. Remember that we, even with our dichotomous variables or categorical variables, we want to take a look and make sure that we don't have outliers, right? We've got a 10-to-1 splits or 9-to-1 splits, right? Where we've got 5 people taking opiates and 250 who aren't. Is opiate use a good variable to have in that model? No, it's problematic, right? So why don't you just take a look at that. Also, what we're going to do, go down through, take a look at descriptives. We'll go pain severity, PTSD total, and role functioning. We'll save as standardized variables. We'll request schema and kurtosis. Continue that.
Which variables are you doing? Sorry, I like to
Yeah, PTSD are 2 continuous variables, PTSD and role function. Pain severity, pain severity, PTSD, and role functioning. So our 3 continuous variables that we're going to go through. You guys can hit paste, I'll hit OK. And again, if you're having a hard time seeing with that stuff up here, it's all sort of on. Okay, you should have, there's a PDF that you can pull off of it.
There's no.
Did I not put one of those on there either?
And I like have everything else from that day.
Okay, yeah, this is, all right.
Sorry.
Do some people have this?
I have
Okay.
a regression, I don't know.
Okay, you might have, I might have brought it in, you might have forgotten to, didn't get it, grab it, so. No, I can't. I do not have that with me.
It's okay.
Are you all right?
Yeah, it's okay.
Okay. So, Alex, do you have yours?
Yes.
Can you sort of let, don't look out with that. Okay. So we've got our descriptive statistics. Sam, what are we looking at here? What are we wanting to see in terms of our descriptive statistics?
Plausible value.
Yeah. Right. Plausible value. So does it look like our variables are falling within expected range based on what we've got on our sheet here in terms of our scaling stuff?
Yeah,
Looks good, yep. So our minimum and maximum falls within the values that we would expect, and so we're looking pretty good in terms of accuracy, plausibility of everything, right? Looks like our categorical variables have pretty even split in terms of opiate use, not missing any variables in values in this set, so feeling pretty good about things up to this point. Yeah?
Can you explain what role functioning is?
Role functioning is the extent to which I'm able to do basic things, right? Can I cook for myself? Can I bathe? Can I run errands? Am I able to go to the grocery store, hold functional interpersonal relationships, things along these lines, right? So the extent to which I'm able to perform daily activities of life. And so what we want to see is what's the unique contribution of pain, PTSD, and medication use on just people's general ability to do some of this stuff. So, going down through, taking a look at that, Lauren, what else do we want to take a look at in terms of these descriptors down here?
The skew.
Okay. Do we see problems with skew and kurtosis?
No.
Anybody see problems with skew and kurtosis? Role function looks kind of wonky, right? I'm not super excited about that. I mean, I've got 200 people, right? And so probably I could say, based on what we've talked about before in terms of sort of how much our regression models can tolerate some stuff, right? You're saying that at 100 people, the impact of negative kurtosis goes away, at 200 positive kurtosis goes away. So probably we're okay, but this is something definitely worth noting, that it looks like rule functioning is not following a normal distribution. You know, a rule of thumb for skew is about 2, but based on this point, if you run through and look at histograms of variables that have skew of 2, do those look anything that's even close to normal? No, it's very clear skew going on there, right? So in terms of just our absolute values, pain severity, PTSD look like they're within bounds. Role functioning stuff is something that I'm probably going to want to keep an eye on. So we can now, actually, we're going to keep this consistent with some of the things that we've done before. So let's go through and under descriptives, ask for explore. And we'll ask for pain severity, PTSD, and role functioning, right? All 3 of these variables, because we want to get graphs for these, and we'll put subject number in our label cases by, so we can get any weird stuff labeled. We can go to statistics plots, plus histograms. Okay. Pain severity looks like a bunch of gappy teeth here, or we've got chunks in between, but not looking terrible, right? In terms of things, looks like we've got something of a negative skew based on our box and whisker plots, some values that are falling beyond 1.5 times the inner quartile range, but probably not anything I'm going to be too concerned about, right? I might note that I've got some slight negative skew when I'm describing this, and say I've got a collection of observations that are falling 1.5 times the inner quartile range below the median here, but probably not anything that's going to catch my interest too much in terms of flagrant violations. What about PTSD scores? That's beautiful. I'm very excited about this distribution of scores here. Right? That's a nice semi-normal distribution. I don't know if you get a better box plot than that, right? We got one value that's falling a little on the high end, right? But doing okay there. This is our role functioning variable. Yikaroozle. That's not great in terms of the histogram, kind of what we would expect, right? If we go down through and take a look at gross, this is a line with a bunch of stuff, right? So what does this, when I look at this, okay, what does this tell me? And again, this starts to become important when I see something like this, wanting to say, hey, what does it mean about our data? What should I infer about my sample based on this plot of role functioning? And that's what the picture is saying. What does this tell me about the functioning of my sample? Yeah. If I'm a clinician, what does this tell me about the functioning of this group of people? It's really bad, right? I've got a group of people who are not doing well, right? If higher scores are indicative of higher levels of functioning, I've got a group of people that almost universally are reporting very, very low levels of functioning, right? And then some people kind of above, but I mean, given the inner quartile range is 0 on this, right? All of these, anything that's not 0 is all more than 1.5, more than over 3 times the inner quartile range for this sample. And so this is something that I should pick up in my screen and say, hey, if this is my outcome, that's fine, but I've got a really, really low functioning sample that's based on this metric, right? People seeing that? Other thing I might want to do is, yeah, what's going on next?
Just a question. Does it matter that all the outliers are like come from one specific area, like in one specific area? So like 3 are in one, 3 are in another, 4 and 4. Like each are in the same place.
You're a genius. You read my mind. Okay. Well, so we're saying. So if you look at the top of the page, we're saying that this the range of scores for role functioning are 0 to 100. Anybody see a problem with this? You nod your head, Sam. What's going on with this variable? Yeah. If you go back to the SPSS file, what are you noticing about the values of role function?
You're in increments of 45.
Yeah, right. So we're treating this like a continuous variable, right? And I say, oh, this is ranging from 0 to 100. So in my mind, maybe my assumption is this is a gradient, right? When we actually look at the level of measurement here, it's not continuous, right? We've got at best an ordered categorical variable that we're treating as continuous, but we've got values. It's not 0 to 100, it's actually got 5 values. We've got 0, 25, 50, 75, and 100, right? And so this is one of the reasons we're starting to get kind of a funky distribution here, right? Like we often will treat ordinal scales having 5 or more values as continuous, but that's not without cost, right? And it's important to recognize that this really is actually 5 values that this can roll on, and it's actually causing some kind of a gross distribution in terms of our stuff. Right? So if we were to want to go through with this, so we might have some concerns about our rule functioning variable, right? Let's go through and take a look and go analyze descriptives. Look at our z-scores. We won't have to save our z-scores of our z-scores. How many people have saved z-scores of their z-scores already? They're constant, right? So go through, cut those off, right? And you got like 70 different variables in your file. Right? It's a good time. So we'll go through, take a look at our distribution of our z-scores. What do we have going on? What are we seeing going on here? What do you think, Stephanie?
Well, we see some outliers for pain severity. They're pretty standard deviations that we see. And we see the same problem with PTSDs, or there might be one case there. It's 3 standard deviations higher. And we see the same for role functioning, but that makes sense given the distribution. Seeing on that spot.
Right. And so again, always be careful with this idea of outliers, right? Here, I would say we might have some extreme scores in terms of pain functioning, right? So we've got at least a couple of people, it looks like, who are reporting low levels of pain within this sample, right? We've got people who are tending to have pretty high PTSD scores in this sample, and then some people who have much higher levels of functioning than I would expect, right? But at the end of the day, at least based on this, are we going to be too concerned about univariate outliers? Probably not, right? I mean, it's a large clinical sample. We're expecting to have some people out there on the edges, right? These scores look like they're pretty closely packed within the distributions, right? And so for this stuff, right? Again, I'm kind of going back and forth in terms of am I concerned about outliers? Probably not in this sample, right? Am I concerned about the distributions in the sample? Maybe, right? Particularly this role functioning variable, it's got a pretty considerable skew. Now, I've got 200 people in my sample, so I can probably handle that a little bit, right? But it's something I want to sort of keep an eye on and be mindful of as I'm progressing through different screening stuff. Right? So, wanted to go up through, and I'm going to go through and look at my graphs. I'm going to go scatter. Oops. That one there. Right? So I want to have pain severity, PTSD, and rule functioning in my matrix plot, right? Because I want to take a look at bivariate relations between these. So I'm going to hit OK. What did we say? What are we putting in here for that ratio? What is it?
500.
500?
Yes.
We won't get too fancy with the other stuff, although we could, right? So if we're looking at our bivariate relations, are we seeing anything that's looking nonlinear? Not really, probably, right? I don't know that I'm seeing any of these that are demonstrating or suggesting a clear nonlinear relation with one another, right? What about homoscedasticity? What do you think, Katie? PTSD and role functioning, or if I look at sort of this right here, right? We're getting kind of a weird, it looks like as role functioning increases, I'm starting to get less variability in terms of PTSD, right? So if I go analyze graphs, let's put this guy up here. Role functioning on my X, PTSD on my Y, and I hit OK. So we're getting, it looks like pretty clear reductions in variability of scores along each one of these. And this is actually, ends up being kind of nice because this is our role functioning variable. It's actually an ordinal variable, right? And so we've got a very clean set for each value of role functioning variability around PTSD. So we've got, it's clearly not the same. Is it enough to cause us a problem? What do you think, Angela? Probably not yet, right? It's clearly there. This is something, if you saw this in an assignment, I would hope that you would notice that this was kind of something that was going on. But again, what's our rule of thumb for being concerned about stuff? What about this 3-to-1 ratio, right, of smallest to largest? This is not 3 times this, right? So probably our model is going to be relatively robust to this, but definitely something you want to call attention to with your screen. And this, I'm kind of going off script with your handout. I'm going to go through. This is an old handout. I'm going to go through and sort of construct the screening piece of this to help you guys, so you have a little bit of a model to go through some of this stuff as well. Last thing I want to go through and take a look at here before we jump into our actual regression model. Look at my bivariate correlations between variables in my model here. And I'm going to go, okay. Any concerns with my bivariate relations? What do you think, Morgan?
None of them are exceeding 0.9. But it looks like opioid use and PTSD are not significantly correlated.
Okay. What else? Nothing's concerning, like it's going to destroy or bring down our model, but what might I notice in terms of bivariate correlations here? What do you think, Stephanie? Yeah, I mean, we got a correlation of close to 0.6 between pain severity and role functioning, right? I mean, that's not a problem necessarily. For psychologists, it's not a problem in terms of redundant variables, but it looks like pain holds a really, at least at the bivariate level, a really strong relation with people's score on this functioning measure, right? And so again, maybe wanting within this, say, not seeing any problems, but are noting a large correlation, bivariate correlation between role functioning and pain severity within the sample. So at this point, we've gone through, we've taken a look at plausibility, we've looked at missingness, we've gone through, we've looked at univariate distributions, we've looked at bivariate correlations, We've looked at our scatter plots, right? We've looked for outliers, things along those lines. Based on what we've done previously, in terms of our general multivariate screen, what have we not accounted for yet? Say it, Alex, say it loud and proud.
Multivariate outliers?
Multivariate, shout it, because otherwise people won't hear it on the thing, right? You don't have to. But multivariate outliers, right? Now this is one of the things, in a general multivariate screen, when we're sort of looking at the sort of relations between all of these, we don't need to go through and systematically set up and regress our predictor, our subject number onto our other variables to try and go through and get our Mulholland distances. We can go through and do that just within the context of our regression model. Because in our regression model, we're saying this is my outcome that I'm regressing onto my predictors, right? And so I can just request Mulholland distance with that. Would be redundant to run my regression model or regress my subject numbers onto my all the predictors in my model, and then sort of then run my regression. So we're going to take a shortcut on here. So what we're going to do is, so we're taking notes of all of this, right? So what I'm going to do now is I'm going to go through, and so what, of all the stuff that we ran, what am I most concerned about probably at this juncture? Rule functioning, right? Is this going to screw with my stuff? Is this something I need to be concerned about, right? So what I'm going to do, I'm going to go analyze regression linear, and I'm going to say I want rule functioning to be my outcome. I want pain severity, opiate use, and PTSD to be my independent variables. And then up in statistics, I'm going to ask for, let's ask for confidence intervals, right? We can change what level of confidence intervals. We just get these directly through PTSD. I'm going to ask for part-partial correlations. I'm going to ask for collinearity diagnostics. We've also already run through our descriptive, so we won't request that. I'm also going to ask for case-wise diagnostics, okay? And what this is going to do is it's going to give me, and we can indicate right here my threshold. I'm just going to leave it at the default, but we're going to look at stuff to get flagged, anything that's more than 3 standard deviations in terms of our standardized residuals. If we wanted to change that to a different value, we could. The default's generally fine, but and that's what we're leaving here. So we're going to continue there. And then also I'm going to go to plots. And I'm going to go my standardized predicted value, and I'm going to put that on my X. My standardized residual, I'm going to put this on my Y. This ends up being kind of crisscross kind of business here. So what I'm going to do is I'm going to plot my standardized predicted values across my x-axis, and on the y values, I'm going to have my standardized residuals. I'm going to hit that. It's going to say, provide that, then I'm going to hit save. And this is where I can request my Mulholland distances right here, right? And what this is going to do is it's going to look at multivariate outliers, looking at the regression of my outcome variable onto my predictors, basically the model that I'm interested in running, right? So we can, here we're running a screening specifically for a regression model, so we don't have to worry about regressing a subject number onto variables in the model type of thing, okay? We go through and hit continue here, and then that pretty much gets us to what we need to do, okay? So you guys hit paste, I'll hit okay. All right, so this is the model that we're going to run just for, we've decided to ignore the problems, potential problems with rule functioning right now, because we're saying it's not great, but our model's probably robust to it, kind of, right? But let's go through and run and take a look and see what happens, right? So going down through and taking a look at my output, Morgan, what am I interpreting here in this table right here?
R squared.
My R squared, right? And what is my, how do I interpret my R squared value?
Can't say I remember off the top.
Give it a shot. It's okay to be wrong. We're all wrong. I'm often wrong. I was just, had a student correct me in my intro psych class. I've been telling people that phonemes are this most basic unit of sound in the language. That's not true. Hasn't been for 6 years, but that's what I've been telling people. Anybody know what a phenome is? And what I was trying to say? Phoneme, yeah, it's phoneme. Phenome is genetic phenotypes and all the genetic phenotypes. I had someone call me out on that. It's good times after 6 years. Yeah. So, there's no shame in being wrong. Be loud and proud with being wrong. So, Morgan, how would you interpret your R squared value?
I know it's a regression coefficient.
Mm-hmm.
It looks good, but I don't know in words, I guess, how to.
Someone help her out? No, this is nice. I like it hearing coming from everybody in a big way, right? Our R squared value is going to be the proportion of variability accounted in our. It's going to be the proportion of variability in role functioning that's accounted for by the best linear combination of pain severity, opiate use, and PTSD. Okay, that's kind of a formal way of saying that the combination of pain severity, opiate use, and PTSD together is accounting for 37.6% of the variability in role functioning within these data. Shannon, what about this adjusted R squared? What's that telling us? What's that?
Was it correct?
Okay, not quite. What are we concerned about our R squared value? Yeah, and why is it biased?
Because if you have a smaller sample size, or I guess with the estimating line would not be as accurate if there were more.
There's always going to be some shared variability just due to randomness, right? And so we know that our R squared statistic at the sample level is going to be an overestimate of the population coefficient, right? But what we want to do, and so we say this becomes particularly problematic in small samples, and so we've got an adjustment with our adjusted R squared that accounts for sample size and the ratio of predictors to observations and things along those lines. And so will our adjusted R squared ever be larger than our R squared? No, right? It's always going to account, we're going to have some shrinkage here. Again, we don't worry too much about our adjusted R squared in psychological science because we're rarely concerned. We probably should be more concerned with maximizing the prediction of our outcome, right? But in some types of areas, right? If I'm running a model that's projecting income or something that's meaningful, where that's something I'm trying to account for, we want to think about that. Here, we're not doing too bad. We get about a 1% decrease in our overall between our R squared and our adjusted R squared, but we've got a reasonably large sample. We've only got 3 predictors. There's not a whole lot. We're not getting much of a penalty within the context of this model, so we don't see too much of a difference there. Okay. So we've got accounting for close to 38% of the variability in our outcome with these 3 predictors. Katie, is this a statistically reliable model? I don't know. Where are we looking? We want to determine whether or not this is a statistically reliable model. Yes, and why is that? How do you know that? Yeah, our ANOVA table here, right here. Remember, there are sum of squares regression, right? This is the difference, or sum of squares total. This is the difference between Our predicted or our sum of squares total is the difference between our individual observations and the mean, right? That variability. Sum of squares regression is the difference between our variability between our predicted values and the mean. Residual is the difference between our predicted values and our observed values. Remember, we've gone through to our sum of squares between, sum of squares within, and our total. If we go through and we run this table, we see that we have a statistically significant F, which leads us to conclude what about our R squared value? What do you think, Alex?
It's reliable.
It's reliable, right? Which technically means what? That our R squared value is
Sufficient enough to adjust.
not quite. What are we always testing? Almost always testing with our hypotheses test. Whether something's equal to 0, right? All this tells us is that our R squared value is something that's not 0, right? Which we probably aren't terribly surprised by that, right? But well, again, if we get into the basic building blocks, we would say, assuming that the best linear combination of pain severity, opiate use, and PTSD total account for 0 proportion of variability in our role functioning variable. Assuming that that's the case in the population, these data would be very unlikely, right? Again, this is getting back into sort of the bare bones, specifically what our statistical tests are looking at. But our ANOVA table here is a test of our R squared, and it's saying that our overall model is accounting for at least some non-zero variability in our outcome. Okay? Now, whether or not we're excited by this or not, I don't know. That kind of depends on the research question. But wanting you to know different pieces and parts and how all this stuff is working together. Okay? Questions about this stuff up here? Okay. Jumping down into our coefficients. Angela, what are we seeing in terms of our coefficients here? If we want to, before we start interpreting coefficients, let's go through and take a look at our collinearity diagnostics. We see any new problems here, Angela? No, why not?
Our tolerance values are greater than 0.1.
Yeah, they're pretty good, right? Again, we start to have problems with tolerance values like 0.5, 0.6, right? It's suggesting quite a bit of redundancy here. We're not seeing any problems, right? It seems as though we have a fairly efficient regression model where we don't have all of our predictors stacked on top of one another. Again, if we look down to our collinearity diagnostics, we don't have any condition indices above 30, right? Our variance proportions aren't overlapping, right? So we're doing good. And we had predicted as much based on our looking at our bivariate relations. But again, in multivariate space, weird stuff can happen, so we always want to go through and make sure we're taking a look at this. If we go down through and take a look at our case-wise diagnostics, right? This is giving us flagging cases with standardized residuals above 3. Okay. Sam, what are we seeing in terms of our case-wise diagnostics? What's that? What are we talking about when we're talking about standardized residuals? So this is another way to look at like kind of multivariate outliers, right? And what it looks like here is we've got 3 cases, and this is the case number isn't their subject number, it's where they're currently, where they're at right now in my file, right? And so it's these last 3 cases right here that are demonstrating standardized residuals that are exceeding 3, right? And so we've got one with a standardized residual 3.2, 3.7, 3.9. These are all cases where the value for my outcome are at the high end of my rule functioning, right? Which I know I have problems with this variable here. So this is going to start to maybe say, okay, I might have some problems in terms of multivariate outliers here, right? If I go down through and I take a look at my residual statistics here, I can go through and I can take a look at my Mulholland-Novus distances, right? So my minimum Mulholland-Novus distance is 1, max is 11.4, okay? And so if I'm saying that I want to take a look at identify multivariate outliers, how do we determine what's something that we might want to take a look at in terms of a multivariate outlier based on our Mulholland-Novus distances? Anybody remember what do we do? Not 30. What's that? Okay. What do we know about Mulholland-Novus distances? How is this statistic distributed? It's on the chi-square, right? And so what we want to do is we want to take a look at, in order, what we want to set a threshold, just like we do for our outliers using our Z statistics, right? We want to take a look at set a critical value, conservative critical value for our Mulholland-Novus distance on a chi-square distribution where the degrees of freedom are equal to the number of predictors. Okay, we have 3 predictors in this case, right? And so if I go through and I take a look for p equals 0.001 on a chi-square distribution for a chi-square with 3 degrees of freedom, I get a critical value of 16.26. So what I would do is I would take a look here and say, do I have any cases with a Mulholland-Novus distance that exceeds 16.26? And I don't. So we've got a little bit of a mismatch, right? We've got cases that have a standardized residual that exceed, you know, if we want to say if we use the same criteria as our Z statistics, right? It would be for 0.001, it would be 3.29, right? And so I've got one case with a standardized residual that would exceed our Z criteria for at alpha equal 0.001. But none of my Mulholland-Novus distances are getting up there, right? And so I'm kind of in this limbo space. Maybe I might want to take a look at, say, no cases registered Mulholland-Novus reliable or identified or met criteria for multivariate outlier in terms of Mulholland-Novus distance with at p less than 0.001. Did find a case with a standardized residual that was pretty high, and might want to note that whatever case is 197 in the order here. Is looking like this is a case that might register as potentially problematic, right? So it's not registering high on Mulholland-Novus distance, but this is someone who got reasonably high pain variable. They're relatively high in pain. They're taking opiates, and they're still reporting really good functioning, right? With moderate PTSD, so or low levels of PTSD. So this is cases looking kind of weird in terms of our outcome, but not anything that's too crazy here. Okay. So again, wanting you to get into this situation where you're feeling comfortable, where we're not following. This is the rule of thumb. This is where it's always this or always that. You're wanting to take a more global approach to these data and say, well, sort of this is a case that sort of kind of fallen out of bounds. But again, at the end of the day, are we too worried about this one case? Probably not, right? Again, given what I know about the distribution of my outcome variable is a little bit weird, so I'm going to expect there's maybe going to be some oddities going on with that. So last thing we want to do in terms of screening here is taking a look at our residual plots. Okay, this is a residual plot for these data. Remember, what I want to do is I want to take my line and run it across 0. Okay. Now, based on my plot here, should I have concerns about nonlinearity of my residuals? Or excuse me, nonlinearity of the residuals, homoscedasticity of my errors, and normality of my errors. What do people think? So I want to draw a line here. Right? Am I excited about that residual plot? No, I'm not excited about that residual plot. What do you see in Alex that might be problematic here that should at least grab my attention? Am I worried about linearity? No. Am I worried about homoscedasticity? Maybe. Am I worried about normality? Yeah. And again, remember, this is a case where our outcome variable, almost everybody's 0, right? And then we've got people trailing down. And so you can see, right, this isn't a nice cloud. You've got people at sort of each one of our predicted values here. But if I draw this line across, got a whole lot of stuff hanging out here as opposed to down here, right? And so, again, I might not be terribly surprised by this, given some of the funky stuff that was going on in my outcome variable. But so I may have concerns in terms of my variability, right? This, so for each one of my across my predicted values, in a lot of variability here, and not a lot of variability here. I mean, it's a not, because my outcome is an ordered categorical variable. That kind of makes it hard to take a look. I certainly wouldn't give this the thumbs up and say, sure, it looks great, let's roll with this, right? So one of the things that we're going to do, and we'll pick this up next time, what might we want to do? If we have some concerns about our outcome variable, what might we want to do? Yeah. Alex whispered it and you said it. Yeah, transform it, right? I mean, technically the distribution isn't bad enough so that we would have a but it's clearly skewed, right? We've got a high, reasonably high kurtosis value. We've got a lot of people in our sample that helps protect against some of this stuff, but it's certainly something we might want to take a look at. Okay, real quick, let's jump back up just because we don't have that many variables in this model. What is our constant telling us, Angela? How do we interpret this constant, our regression constant?
That when the variables are 0, then we would expect severity to be 67.
So it's function.
Oh, sorry, yes.
Right.
I
So
wrong
with PTSD score at 0, with pain score at 0, for people who are not taking opiates, right? And so in our dichotomies, this is where it starts to become important, where we put in 0, 1 coding, because if I code this 1, 2, it doesn't make sense to have someone at 0, because that's not a real value. But if 0 is no opiates, 1 is opiates, right? I'm saying for people with a pain score of 0, with no PTSD who aren't taking opiates, we would expect a functioning score of 67. Same thing here, we would go through and we would say, based on my unstandardized coefficient here, for every unit increase in pain severity score, I would expect a 10.7 point decrease in reported functioning. For opiate use, someone take a crack at opiate use. What is this coefficient telling me?
Isn't it for every, compared to people not taking opioids, those who are see a decrease in role functioning of about -0.6?
Absolutely, very good. This is a dichotomous indicator, right? So the difference between in role functioning between people who are taking opiates versus those who aren't. Those who are, when we go from 0 to 1, because that's the only 1 point increase, unit increase we can take, we would expect about a 0.7 reduction in role functioning. Now, role functioning is 0 to 100. Is this a big coefficient? No, right? And if we take a look at our our significance value, that's not anything, right? So based on this, it looks like opiate use has no unique association with our outcome once we account for PTSD and pain. Here, PTSD score, our unstandardized coefficient, we would say that per unit increase in PTSD score, we would expect about a 0.23 unit reduction in role functioning. This seems not big at all, right? But remember, our PTSD scale runs from 0 to 136. Our functioning goes technically from, conceptually from 0 to 100, right? And so even though that's not a lot, as we start to increase the number of points that we would get, right? So we see that pain and PTSD hold unique relations or unique associations with role functioning. Opiate use does not. If we look at our standardized coefficients, which one of these predictors is carrying the day, Katie? Take another look. In terms of our standardized coefficients? Pain severity, right? So again, if I was looking at this, right, and we can go in and we'll talk about part and partial correlations and things like that next time. But overall, what I would glean from this regression model here that's not without its warts would say that both pain severity, both physical pain and post-trauma symptoms hold unique relations with role functioning. However, within the context of these three variables, it looks like physical pain holds a much stronger relation with how people are out there functioning than does PTSD, right? And this is something that comes up if you work in this area. People say, oh, emotional functioning or emotional difficulties are the worst. Not in this population. Pain, like I'm in constant pain all the time, like that trumps the day. Like I can't do activities of daily living if I'm in constant pain. It's also hard if I have high levels of PTSD, but we're seeing here clear impact of pain to a greater extent than PTSD. So let's leave it at that. We'll pick up and finish up the last of this next week, and then we'll jump into moderation stuff.